We're going to talk about relative velocity today, and now the way the book does it is different than the way I do it. They kind of give the more formal, traditional explanation, which I remember studying that in college and finding it very confusing. So I think I've got an alternative way of looking at it, which I think will make sense to you and help you do problem solving. But we'll also take a look at what the book did, and we'll do all this in 20 minutes. Okay, so a long time ago, one of my AP Physics students was a young man named Garrett Olson. And Garrett Olson was one of the premier pitchers in our area. He's a baseball pitcher. And he went on to Cal Poly, got a mechanical engineering degree, and played for Cal Poly's baseball team. In fact, he got so good that the Major League Baseball drafted him out of college, and he is a Major League pitcher. He's a left-hander, and he's had some injury problems and all that. But I mean, the fact that you can pitch at that level is just a staggering achievement. So I'm going to use Garrett as an example. Suppose Garrett, here's the ground. Now this is how I draw the ground. Whenever I draw a straight line and draw little hash marks like that, that means, okay, this is the ground. It's fixed. It's not moving. But on the ground here it's on a train track. I'm not going to draw the tracks, but imagine you've got a flatbed train. And, and so here's Garrett. Well, I'm not going to say this is Garrett because it's not going to do him justice, but standing on the edge of this train, and he throws a ball like this. So here's the ball coming out of his hand. Now let's ignore gravity for right now. Okay, let's just assume that, this is the velocity. Now, let's say that he throws the ball, and the velocity of this ball is maybe 50 meters per second. Well, let's use miles per hour. That's okay. We can use miles per hour. So let's say he throws it and it's going 80 miles per hour. Okay. Now, standing over here on the tracks is an individual who's going to try to catch this ball. There's their mitt. They're going to try and catch this ball. Now, let's suppose they're not really standing on the tracks. They're standing off to the side, but we're not going to worry about that so much. Let's say the train is moving. So, the train is actually moving 40 miles per hour. So my question to you is, how fast is that ball actually moving? I mean, what do I mean when I say I'm throwing the baseball, or Garrett's throwing the baseball at 80 miles per hour? Where am I measuring that velocity from?
Like from on the train ground?
You see that it makes a difference, right? I mean, is this 80 miles per hour with respect to the train, or is it with respect to the ground? You see what I'm saying? I mean, it matters, doesn't it? Okay. So we have to say what our velocity is relative to, or with respect to. Okay, and that's what we're going to talk about today, is how to solve problems where velocities are, it depends on what reference frame you're in. I mean, if I'm standing here on the ground, and he throws at 80 miles per hour, but he's on the train, and the train's moving 40 miles per hour, is this ball actually moving 120 miles per hour? Or is this 80 miles per hour, is he actually throwing at 40, and this is, so the 40 plus 40 gives me the 80. So you have to say what it's with respect to. So what I'm going to do is this. I'm going to say I'm going to come up with a notation here. And I'm going to say that this 80 miles per hour, this is the velocity of the ball with respect to the train. So I use this little, and this is what's a little different than the book. I say what the velocity is measured with respect to. The ball is moving with respect to and T stands for train here. The ball with respect to the train is moving 80 miles per hour. Now, what is this 40 miles per hour? What is this? This is the velocity of the train with respect to what? The ground. And that's going to, and I'll use G for ground. And that's 40 miles per hour. So now I'm going to come up with a relative velocity equation that makes total sense, okay? It really does when you look at a simple problem like this. Now, when we get to more complicated problems, it's going to be confusing, but it's really the same thing. It's just saying, hey, the velocity of the ball compared to the ground is equal to the velocity of the ball compared to the train plus the velocity of the train compared to the ground.
You just add two velocities.
Doesn't that make sense? Okay, the velocity, here's how fast the ball is going compared to the train here, but the train is moving this fast, so what do I do to these two velocities to figure out how fast it's going with respect to this guy who's not moving at all? I add them. Okay?
Because they're like two vectors in the direction.
Well, that's a great question. They are vectors. See, and here's the thing to remember. Velocity is a vector. This is a vector equation. Now, sure, in this case, the velocity of the ball compared to the train and the velocity of the train have the same direction, right? They're both moving down the track. But it doesn't have to be that way. And even if it isn't that way, I can still use the idea of this vector equation. What's different than the book is this little notation right here. The ball compared to the ground, ball compared to the train, train compared to the ground. So the velocity of my now here we're going to talk about reference frames. A reference frame is a coordinate system that you measure things with respect to. Now here we have a coordinate system on the train. You could have an observer sitting here on the train and making measurements of position and velocity and acceleration. Or you can have an observer here on the ground making observations of position, velocity, and acceleration. So those are two different reference frames. Okay? Reference frames are observers that measure things, position, velocity, and acceleration. But maybe those observers have different velocities. Now here's one thing you have to know about a reference frame. We're going to call them inertial reference frames. Your reference frame cannot be accelerating. So your observer on the train cannot be accelerating on the train. Or your observer on the ground cannot be accelerating. So if you have a reference frame for everything to be good, that reference frame cannot be accelerating. And we'll talk a little bit more about that later. But for now, I'll just leave it like that. Well, what if Garrett, standing on this train, instead of throwing the ball forward, he throws it sideways with respect to the train? No problem. Let's redraw the picture. Let's look down on the train track. So here's the velocity of the train. Now, here's one thing I'm going to do because I'm lazy. I'm not going to put with respect to the ground. I'm just going to leave it off. If I say v sub t, that's the velocity of the train with respect to the ground. Now, here's Garrett, and let's say he throws the ball like this. And this is the velocity of the ball compared to the train. Now, what if you're on a helicopter that's stationary with respect to the ground? In other words, you're really a ground observer, but you're above, and you're looking down on this, and this train is moving like this, and he throws the ball like this. For you, what's the ball going to do? What's the direction of the ball going to be? Yeah, it's going to be, well, this equation tells me. The velocity of the ball compared to the ground is going to be the velocity of the ball compared to the train plus, well, here's the velocity of the train, plus the velocity of the train. So the ball is actually doing this compared to the ground. So here's the velocity of the ball. I can go ahead and put compared to the ground, compared to the ground. This idea of saying the velocity of my object compared to my stationary reference frame will be equal to the velocity of my object in my moving reference frame plus the velocity of my moving reference frame, with respect to my non-moving reference frame. Okay? You see, it's fun to play with this. Any of you played on an escalator before? Okay, so there's a moving reference frame. You stand, if you walk onto the escalator and you stand on the escalator, and the escalator is just taking you up, your velocity compared to the escalator is 0. But your velocity compared to the ground is whatever the velocity of the escalator is. But let's say you're in a hurry, right? So you walk up the escalator. So your velocity compared to the store, or the mall, or wherever you are that has an escalator, your velocity compared to the ground will be equal to your velocity compared to the escalator plus the velocity of the escalator itself. Doesn't that make sense? Have you ever tried to go down an up-moving escalator? Oh, of course you have. Did you ever have a mall cop come after you and say, "Yep, yeah. Yeah. Oh, darn it." So, so that's what's going on here. If you are in a moving car and you throw a ball or something out the moving car, this is the situation that you have. By the way, if you're in a moving car and you're in the back seat and your brother's in the front passenger seat, and so you throw something at your brother or whatever, your friend, what's the velocity of the ball? Well, compared to what? You have to say. Compared to you, maybe it's like 3 meters per second. But compared to the ground, maybe it's 50 meters per second, depending on how fast your car is moving. Okay? Yes. So, in other words, velocity is relative. Now, here's, this triangle is the key to solving all these problems. Drawing this triangle. Based on what's given, you have to read the problem very carefully and figure out what's given. And figure out, because here's what you can do. The velocity of the ball compared to the train. Well, it's going to have a speed and a direction, isn't it? So you could have a problem where they give you the speed, but they don't give you the direction. The velocity of the train. They could do the same thing. The velocity of the train has a magnitude and a direction. And then the velocity of the ball has a, has a speed and a direction to it. This is the ball compared to the train. This is the train. This is the ball. Okay? So when you work a problem, here's a strategy. When you're working a relative velocity equation, figure out what the ground is. It's usually just the ground. Figure out what your moving reference frame is, and then figure out what the object is, and figure out what they're giving you. And there are 6 different things they could give you. Then take what you're given and try to draw this triangle from it. Now, by the way, if the moving reference frame and the velocity of the object in that moving reference frame are lined up, it's not going to make a triangle, it's going to make a straight line. Okay, when you add up the vectors. But chances are, the problems, I mean, this is AP physics, so chances are these things are not going to be lined up. And they'll give you, any one of these, but they will give you enough information so that you can construct this triangle. And of course, once you have a triangle, you can solve any vector equation. Okay, so you can take this, draw this triangle, get these 3 vectors in ij form. Now this, I wouldn't even use ij form because this makes a right triangle, but it doesn't have to make a right triangle. I mean, what if Garrett threw the ball at an angle with respect to the train here, and then now we've got to add this, and so now it looks like that. It's not a right triangle, so you can't use right triangle math. You have to use ijk, unit vectors, to break up the vectors into their components. Okay. Now, what kinds of problems are you going to be given here? Well, there's the train problem. But there's also river problems. Let's suppose here's a river, like here's a bank, and here's a bank. So the way I show that is I draw my hash marks like this. So, I'm sorry, here's a river, and you have a velocity of the water. So I call it V sub W, the velocity of the water. And then maybe you have a boat. And this is the velocity of the boat compared to the water. Now, what they'll quite often do is they'll give you a heading. Like they say, a boat is heading 50 degrees north of west or something like that. Well, that's the direction. If they give you a heading, that's the direction the navigator is pointing the boat. Does that mean that's the direction the boat is actually moving in? No, because the boat is pointed this way, and it thinks, and compared to the water, it's actually moving like this, but the water is also moving like this, so compared to the ground, the velocity of the boat itself will be like that. Okay? So constructing this triangle and knowing what's given is what makes these problems confusing and difficult. But if you just break it down and do, okay, where's the ground? What's the moving reference frame? And what is given in terms of the, do they give me the final, sometimes they give you the final velocity, magnitude and direction of the final velocity, and you have to figure out what the velocity of the moving reference frame is. If you draw the picture of the triangle, you'll get it. If you don't, if you try to use pure math, you're going to get confused, and you'll be unhappy, and you'll do cruel things to your dog or whatever. So another problem is an airplane problem. So here's an airplane. We'll look down on the airplane. So this is like a jetliner. Okay, and here's this, and here's the tail. And maybe it's flying through the air. So this would be the velocity of the plane, I'll use P for plane, with respect to the air. Maybe the air is moving like this. So this is the velocity of the air. Now, if you're the pilot, you better account for the velocity of the air if you want your plane to go in the right direction. Or you want to know how long it's going to take you to get somewhere. Because here's the triangle. The velocity of the plane with respect to the air plus the velocity of the air will get me the velocity of the plane with respect to the ground, which I'll just call V sub P. So there's my triangle. So you have to look at the problem, say, what am I given? If they give you a heading, either as a pilot in an airplane or a navigator on a ship, if they give you a heading, that's the direction of the velocity of the of your object with respect to the moving reference frame, the water or the air. Now sometimes they'll say, no, the velocity of the plane must, actually what you want to do is you say, I want my airplane to fly due north. Okay, that's what I want it to be. So what they're saying, we want this velocity of this plane to be due north. So here's the velocity of the plane is due north. And they say the wind speed is like this. So you know that the velocity of the plane with respect to the air plus the velocity of the air, so you construct the triangle. You have to construct this vector, the velocity of the plane with respect to the air, plus the velocity of the air will get you this. But sometimes they give you this, and you have to figure out, how to draw this triangle. And I'm telling you, if you can draw the triangle correctly and then apply vector mathematics, you'll say, okay, velocity of the plane equals velocity of the plane compared to the air plus the velocity of the air. You've got it. You can solve the problem. Now we're running out of time, so I didn't have time to get to what they did in the book. And it's a little bit confusing. Here's the diagram in the book. Here's where the object is located. Here's, S prime is the moving reference frame. S is the stationary reference frame. And here R is your position vector, and then they take the derivative of it. And it's good stuff to know. And if I had time, I'd go over it with you. But let me zoom all the way out so you can see the whole thing. This is the key right here to figuring out relative velocity problems. So good luck with them. Try to have assignment 3 and 4 ready to be whiteboarded on Thursday. That's all.